Hundreds of millions of years ago, the Earth was covered by vast, shifting wetland ecosystems. In these shallow pools, aquatic life hit a biological ceiling. Waterways frequently grew crowded, oxygen poor, and prone to drying out entirely. For early vertebrates, survival required doing something completely new, breathing air and walking on dry ground. Making that transition demands a violent physical overhaul. During metamorphosis, an amphibian's body literally consumes itself. The gills that extract oxygen from water collapse, dissolving directly back into the animal's own bloodstream. Flexible cartilage ossifies into heavy bone. The skull tightly fuses together. Eyelids form to block wind, and delicate primitive lungs inflate inside the chest cavity. This process drains an immense amount of energy. While its skeleton rebuilds and digestive tract rewires, the animal is left physically exhausted and highly vulnerable to predators. Conquering the land requires paying a massive caloric and structural toll. But if the cost of adulthood is so high, there is an alternative strategy: refuse to pay it. Deep in the dark, isolated lakes of central Mexico, one species took exactly that route: the axolotl. Its body contradicts everything we expect from an adult amphibian. Most noticeably, it retains dense, feathery external gills branching outward from the back of its head. It also keeps a broad, flat juvenile tail fin running along its spine, a structure optimized entirely for generating thrust underwater. Instead of adapting its body for a terrestrial environment, the axolotl halts the biological programming inherited from its ancestors and stays exactly where it is. This phenomenon is known as neoteny. It occurs when an organism develops fully functioning reproductive organs while still maintaining its physical larval form. Because its thyroid gland lacks the specific hormone triggers needed to initiate the physical change, the axolotl reaches sexual maturity without ever undergoing metamorphosis. This timeline tracks a standard amphibian against the axolotl. While frogs push through distinct stages, losing gills and restructuring jaws, the axolotl's physical development flatlines. Shifting this into a bar chart, the advantage becomes clear. Skipping heavy bones and lungs generates a massive caloric surplus. All of those saved calories are immediately redirected. The animal scales up its existing larval body, growing larger, faster, and becoming an apex ambush predator in its aquatic environment. Remaining in a permanent juvenile state is a highly efficient biological strategy that maximizes energy retention and growth. Keeping that developmental window open yields a secondary physiological advantage. The axolotl possesses the ability to regenerate complex biological tissue flawlessly. As we see in this diagram, the animal's body is saturated with unassigned stem cells. When tissue is damaged, these cells cluster at the injury site and behave exactly like embryonic tissue, rapidly differentiating into whatever specialized cells are needed. Instead of sealing a wound with rigid scar tissue, the injury site forms a mass of actively dividing cells called a blastema. This cellular engine allows the axolotl to regrow entire severed limbs from scratch. Over a few weeks, it reconstructs perfectly mapped bone structures, muscle fibers, and completely functional neural networks. This capability even extends to life-sustaining organs. The animal can repair structural damage to its central nervous system, successfully bridging the gap of a crushed spinal cord to restore full mobility. It can even regenerate missing sections of its heart ventricle and portions of its brain, integrating the new tissue with zero long-term loss of cognitive or motor function. By locking its body in a permanent state of early development, the axolotl maintains access to the cellular tools that allow it to continuously repair fatal damage. Zooming out from the cellular level to the macro environment, we find the lake systems of central Mexico. These are deep, highly isolated waters. In these stable waters, a heavy skeleton and tough, sun-resistant skin are entirely unnecessary. Instead, the axolotl's soft, buoyant body is the ideal physical form for gliding freely through a liquid environment. Equipped with specialized sensory organs and a wide mouth that generates sudden suction, it easily consumes worms, various aquatic insects, and small fish, securing its position at the top of this specific food web. While terrestrial amphibians must contend with droughts, temperature spikes, and a high-gravity environment, the axolotl rests in the suspended weightlessness of its deep-water habitat. But this extreme specialization creates a paradox. The axolotl thrives precisely because its environment has historically never forced it to leave. Its survival depends entirely on the lake's remaining stable, clean, and undisturbed. Most of the natural world is driven by a constant pressure to grow, adapt, and colonize new environments. The axolotl proves that sometimes the most effective survival strategy is absolute biological stubbornness.